In this video I'm going to be going over the assignment 32 notes, and this assignment deals with rational functions. We'll basically lay a foundation for a good understanding of rational functions, and then when we get to assignment 33 we'll actually be graphing rational functions using all the things we learn in this lesson. So let's go ahead and get started. It says rational functions. A rational function is a quotient or division of two polynomials. Graph the function by plotting points. Now this is what we do anytime we run into a new function that we don't know when we don't know what the graph looks like. So let's just start picking some points or some values for x. So let's make an xy chart. And so first of all, we know that x can't be 0 because that would make us undefined. We've looked at this function before. We know a rational function is undefined anytime the denominator is 0, and so we need to avoid x values that cause the denominator to be 0, and that would be 0 here. So let's go ahead and pick some nice x values like 1. Of course, if you put 1 in, it will be f of 1 is 1 over 1, and that's just 1, and so our first point is the point 1, 1. Let's go ahead and plug in 2. So that's going to be 1 over 2, or a half. And if we plug in 3, we'll get 1/3, 1 over 3. Alright, so let's put those points on the graph. I want you to notice that they're getting closer and closer to the x-axis. So if I plugged in 4, I'd be at 1/4, and then I'd have 1/5 and 1/6, 1/100th, 1,000th. So we're going to get closer and closer, but we're never going to get to the x-axis. So we're going to go ahead and put a dotted line here, and our line, our graph, just approaches that line and it never crosses. This is what we call an asymptote. That's the line y equals 0, and we make it dotted. It's like a guide when we draw the graph, and we call this a horizontal asymptote. Alright, so let's plug in some more values. Now notice to the left of where x equals 1, it would be nice to know what's happening when x is like a half. And so let's look at some fractions. So let's let x equal a half. If you plug in a half into the function, you get 1 over 1/2. Well, this means 1 divided by a half. And with fractions, when you divide by a fraction, that's the same as multiplying by the reciprocal. And so we get 2. So 1 divided by a half is 2. Another way to say that is how many halves are in 1, and that would be 2. So we get 2 when we plug in 1/2 for x. Similarly, if we plug in a third, we would get 3. And so let's go ahead and put those points in. And you can see what's happening here. If we plugged in 1/4, we'd be at 4, 1/5, we'd be at 5, and that would continue. We'd get closer and closer, but we're never going to get to that line there. That would be the vertical line, x equals 0. This is what we call a vertical asymptote. In fact, we know that x cannot be 0 for this function. Alright, so let's plug some negative values in. How about -1? 1 over -1, we're going to get -1. If we plug in -2, we're going to get 1 over -2, which would be -1/2. You plug in -3, you get -1/3. Now remember, if we plug in a fraction, like let's do -1/2, it's going to be just like what we did with 1/2, except for we're going to get -2. And similarly with -1/3, when we plug that into the function, we're going to get -3. So let's go ahead and graph these points. So I graphed -1, -1, -2, -1/2, and -3, -1/3. And you can see again the same things happening as we get closer and closer to the to the left. As we get closer and closer, or as x gets bigger, -4, -5, and so on, we're going to get closer and closer to this line y equals 0. And so again, we have that horizontal asymptote that we used as we draw the graph. It's a guide as we draw the graph. If we look at -1/2, we're at 2, and -1/3, we're at 3. And so again, the same kind of thing is happening that happened on the other side when our x values were positive. And so this is the graph of the function f of x equals 1 over x. And only thing I want to add to what we already done here is let's write our domain. So basically that's going to be all real numbers except for 0. X can't be 0, so negative infinity to 0, and then 0 to infinity. All right, let's move on. It says, consider the following rational functions and their corresponding graphs. Determine the domain for each function. So if you look at number 2, we're wanting to see when the denominator is 0. So notice x can't be 1. And so that's what we call our restricted value for this function. And our domain is everything else. Now notice sometimes people will look at the numerator and they're like, well, if x is 0, that might be a problem. But if you have 2 times 0 in the numerator, you have a numerator of 0. 0 divided by any number is actually 0, which is perfectly good. We only have a problem when we have 0 in the denominator. So we don't care about the numerator at all when we're looking for the domain. All right, so on number 3, let's see, we need to find out for what values of x does the denominator equal 0. So if we factor that, we get x plus 3 times x minus 2. And so now it's easy to see that negative 3 and 2 are going to be restricted values because they're going to cause the denominator to be 0. So x can't be negative 3 or 2, and that's going to be where we have, that's going to cause us to take those values out of our domain. Basically, negative infinity to infinity, we're going to go left to right. So notice we go to negative 3 first, and then we can include negative 3. And then we go from negative 3 to positive 2, and then finally from 2 to infinity. In fact, you could draw a number line, and at negative 3 and at 2, we have holes. But everything else is perfectly good. Every other value can be plugged into this function except for those two values. So those values are not part of the domain. All right, and then number 4, of course, x can't be negative 2. And so that's going to be taken out of our domain. It's everything except negative 2. All right, let's go ahead and look at the graphs down below. It says, look for asymptotes on the following graphs of the above functions. So basically, I've graphed each function directly below it, and I want you to look for patterns. So let's go ahead and look for asymptotes on the first function, or the first graph here. So notice there's a vertical asymptote right there at x equals 1. And there is a horizontal asymptote there too. Notice right there at y equals 2. We have a horizontal asymptote. All right. So again, look at the function above, look at what we have below. We're looking for a pattern here. All right, so on the second graph, notice these are my vertical asymptotes. Now, if you look at that function up above, you ought to see something there. As far as horizontal asymptotes are concerned, notice we have one at y equals 0 here. You know, and the thing you should notice about these horizontal asymptotes is when it comes to the end behavior, that's where those horizontal asymptotes come into play. As x gets really big or x gets really small, the graph's getting closer and closer to the horizontal asymptote on each end. All right, and then let's look at this last graph. Notice at x equals negative 2, we have a vertical asymptote. And again, you ought to see the pattern by now. Look up above. Notice that's where our restricted value is. There is another asymptote here I'll mention. That's this one here. There isn't any horizontal asymptote, but there is this one here. We call this an oblique asymptote. But we won't study those in this course. But if you move on to pre-calculus, you'll get to work with those and above regular calculus. All right, so there's a pattern going on here. Do you see the pattern? Let's move on to the next page or slide, and we'll summarize here. So I'm going to go ahead and put in the asymptotes that we just found, the vertical asymptotes. And you notice a pattern here. For those, it says for those values of x for which f of x is not defined, what do you notice about the graph? Well, what I hoped you would see is that there's a vertical asymptote. So wherever we have a restricted value, or for whatever x values the function's not defined, we have a vertical asymptote. So an asymptote is an invisible line that the graph of a function approaches. For a rational function that's simplified, if the function is undefined at x equals a, then x equals a is a vertical asymptote. So basically, wherever we have a restricted value on a rational function, or for a rational function, that's where we're going to have our vertical asymptotes. All right, so let's use that rule. It says, write the equation of any vertical asymptotes for each of the graphs of the following rational functions. So on number 5, you can see that x can't be 5. That's my restricted value. And so that's where we're going to have a vertical asymptote. Now, how do you find vertical asymptotes? Really, all you have to do is set your denominator equal to 0. So I could have done that on number 5. I could see x minus 5 equals 0. I want to know when my denominator is going to equal 0. When I solve that, I get x equals 5. And so that's where we're going to have vertical asymptote. So you can always set your denominator equal to 0 and solve for x. And that'll tell you your restricted values, and it tells you also where your vertical asymptotes are. So on number 6, let's go ahead and do that. We'll set our denominator equal to 0. And let's see, we're going to have to use the AC method here. We can take the shortcut because that is a 1x squared. So we need two numbers that multiply to negative 8 and add to 2. That's going to be 2 and negative 4. And so let's go ahead and plug those numbers in. So you can see that x equals negative 2 and x equals 4 are going to be our restricted values. A lot of times what we like to do is just factor our denominator and replace the denominator with the factored form. And it's pretty clear now that that x can't be negative 2 and x can't be 4. It's going to cause your denominator to equal 0. If you plug in 4, you'll have 4 minus 4 on the second factor. And that's 0, and 0 times anything is 0. So either of those two values would create or cause your denominator to be 0. And so those are our restricted values, and that's where we're going to have our vertical asymptotes. The other thing I want you to notice here is we're always writing them as equations. A vertical asymptote is an equation x equals some number because it's a vertical line. And similarly with horizontal asymptotes, it's going to be an equation y equals some number. All right, so on number 7 and 8, you may want to try these if you haven't already and see if you can figure out what vertical asymptotes we're going to have, if any. So when you set x squared plus 9 equal to 0, let's see, we need to get that 9 on the other side, or subtract 9 on both sides. We'll take the square root of both sides, and square root of negative 9 is 3i. So we're going to get plus or minus 3i. Now these are imaginary numbers. When we're doing graphing, everything's real numbers. We don't ever graph imaginary numbers on the real or on the xy axis. It's always real numbers. So what this tells us is x could be anything in the denominator. We're never going to get 0 in the denominator. And so there are no vertical asymptotes. There are no restricted values. All right. On number 8, let's see, we need to know when x squared minus 7x is going to be 0. Here we have a GCF of x, so let's factor. And so x equals 0 and x equals 7 are the two solutions here. And so that's your restricted values. And again, I can write that denominator in factored form. So 0 and 7 are restricted values, and that's also where we're going to have our vertical asymptotes. All right, horizontal asymptotes. It says as x gets very large, both positively and negatively, the graph of a rational function usually approaches a horizontal asymptote on each end of its graph. That's what I was saying earlier. Consider the following function in the corresponding table of values. So, as you look in the table, as x gets really big, 10, 100, 1,000, our y values, or f of x values, get closer and closer to 0. And it happens on both ends. And so this is very common. This is what normally happens with rational functions. It says there are 3 cases for horizontal asymptotes. And in fact, these are 3 cases where we do a little more work. We're basically going to give you the rules here. In calculus, you would actually do some proofs to see these rules, and you'd have to put a little more work into figuring out what your asymptotes are. But we're just going to use the rules. So it says if the degree of the numerator is less than the degree of the denominator, then f has a horizontal asymptote at y equals 0. So for the example here, oops, I forgot to highlight that. The numerator has a degree of 1 because it's x to the first. The denominator has a degree of 2 because x squared is my highest power of x, which has a degree of 2. So you can see that the numerator has the smaller degree. This is what we sometimes refer to as bottom heavy, and in this case we have an asymptote at y equals 0, horizontal asymptote at y equals 0. In case 2, the degrees are the same. That's what they're saying there. And it says the y is equal to the coefficient of the leading term in the numerator over the coefficient of the leading term in the denominator. Let's do the example to see that. So notice the degree of the numerator is 1 because it's x to the first, and the same thing in the denominator. And so this is the case that we call balanced. And in this case, we're going to use y equals, and now look at the coefficients of the leading terms, 2x and 1x, or just x. We're going to write that ratio 2 over 1, which is going to be y equals 2. So you just take the coefficients, or the numbers in front of the leading terms. All right, case 3. So this time, in these cases, the degree of the numerator is the larger degree, or the bigger one. Notice here we have degree 2 in the numerator and degree 1 in the denominator. This is the third case, and this is what we call top heavy. The degree in the numerator is greater. And so this is a case where there's no horizontal asymptote. All right, so let's go ahead and look at problems 9 through 12 where you're finding vertical and horizontal asymptotes. So on number 9, let's see, the degree of the numerator is 0, a constant has a degree of 0, and the degree of the denominator is 1. And so this one is what we call bottom heavy, and so y equals, oh, I'm sorry, I need to do the vertical asymptote first, and that's at my restricted value, which is 4 here. X can't be 4. So at x equals 4, we have a vertical asymptote. And then, like I said before, this one is the bottom heavy case. It was the first, it's just like the first problem we did, the first example. And so y equals 0 is going to be your horizontal asymptote. All right, so on the second problem, number 10, we're going to go ahead and set our denominator equal to 0. And this is similar to one we did up above, or a little bit earlier. We're going to get 2 imaginary answers, which means there are no restricted values, and so there are no vertical asymptotes. As far as horizontal asymptotes, this is the balanced case because they're both degree 2. X squared is your highest power of x in the numerator and denominator. And so now we're just going to use the coefficients, 5 over 1, which is 5. So that would be the balanced case. That's case 2. Let's look at number 11. So again, we want to set our denominator equal to 0. So that's going to happen. We basically have to factor using the AC method there. And so -5 and 7 are restricted values, and that's where we're going to have our vertical asymptotes. In terms of the horizontal asymptotes, notice both of these are degree 2, the numerator and the denominator. Be careful, in the numerator the leading term is -3x squared. So we're using -3 over 1. And so -3 over 1, that's going to be 3. Y equals 3. I'm sorry, y equals -3. You do have to take the sign there. Number 12, so we want to find out what value of x causes our denominator to be 0. So set your denominator equal to 0. We need to subtract 3 on both sides and divide by 2. You get -3 halves. And so that's our restricted value, and that's where we're going to have a vertical asymptote. And this one is top heavy, and so this is the case where we have no vertical asymptote. Notice the degree of the numerator is 3 and the degree of the denominator is 1, and so we are top heavy and there is no horizontal asymptote. Alright, so we're going to stop the video there for now. We'll talk about intercepts and x and y intercepts the next time we meet.